Can you hear me? Hello?
Yes, sir.
Yes, sir.
हाँ, वो म्यूट अनम्यूट को कल गुलमाल हो जाता है. एक मिनट. Okay, I want to continue first countability. So first let's see. Let me give the formal definition of first countability again. So you have a topological space X tau, and you have a point in X, big X, and this is the family of all neighborhoods. Our neighborhoods are open. Neighborhoods of X in X. This is called two things, either neighborhood system or neighborhood. There is a reason that there is a concept of filter in set theory and topology. So it is actually filter. So neighborhood filter at X. Okay. So that this is this thing. Now I want to define a local base. At X. Basically, it's a sub collection of this. First of all, first let me explain that. First, it's a sub collection. Actually, from which from Bx we can recover the whole thing. So, the definition should be that given U belongs to Nx, I am only fixing my mind on X, the point X, nothing else. Even there exists B belongs to Bx such that everything is in the neighborhood of X such that B subset of U. Okay. Suppose you have it, then Bx is called a local base at X. Okay. So that then Bx is called a local base at X. So let me write this definition again. So definition is let X tau be a topological space and X belongs to X. Let it's got non-empty family. This I already explained. This is neighborhood systems at X. If given, then Px is called a local base, local, because we are only putting at attention at X. That's why it's called local. That is a concept of global base that I will do later on. That's why it is called first countable related to local base, and related to global base, it is the concept is second countable. Then Bx is called a local base at X, local base at X, if given U belongs to an X, there exists B given there exists B belongs to Bx such that you sorry such that P is contained in U. Okay. In fact, intuitively later on you'll understand a topology will be finer, a good topology, if you have smaller neighborhoods. Big neighborhoods actually don't help. Okay, so the smaller neighborhood. So basically I am going for a smaller neighborhood if you have it. Okay, and from this you can recover the whole system, neighborhood system, smaller collection. Like example I am giving you, if you take a metric space XD, which is a topological space, yet the topology will be generated by D, then you look at this. Given a point, you are taking a point, X belongs to X. First, you don't need to take this. First, you take just PXR. R belongs to R. This is a local base at X in this. But local base need not be unique. Like here, again, I'm telling you, if I take this, the R belongs to this. These are also will be local base. Look, PXR, R belongs to Q, rationals. This is also a local base at X. Again, this one also. This actually we usually take 1 by n. N is a natural number. This is also a local base at X. So local base need not be unique. In fact, you should always try to have a local base which is very convenient for you to use. Here in metric space, this one is very useful because this gives a sequence. But now look, this is uncountable because this is uncountable. So this local base is uncountable. Uncountable because here uncountable number of neighborhoods are here. But here this is countable since Q is countable. So this is countable. Similarly, this is also countable. So first countability means if each point has a countable local base. Countable local base. First of all, I defined local base. Okay. And then the members of this called basic neighborhoods. Basic neighborhood. When you talk about a basic neighborhood, that means basic neighborhoods at X. That means you have already picked up a base, local base at X, and those members of that neighborhood, that local base, we call it basic neighborhoods at X. Like if you choose in, then it will be called a basic neighborhood of X. Similarly here, basic neighborhood of X. Now, so that with this definition, first try to understand local base. But if you have a countable local base at X at each point, then it is called first countable. So next definition is this. Let X tau be a topological space X, then X tau is called first countable. First countable. It's called the countable action. First countable. If each point of big X has a countable local base. Okay, so every metric space, first example, every metric space xt is first countable. Since this collection, you could take rationals also. Px1 by n, I am taking basically we work with this and in the metric space. Is a countable, sorry, is a countable local base, the countable local base at x. For each x in x. Okay, so every metric space is first countable. But let me tell you that last time I put a left an exercise. Give an example. Of a first countable space which is not a metric space. For the real understanding of this counterexample, you need to wait a while. But I am just mentioning in that. I again come back, I will talk about this, that which is known as surgeon-free line. I'm just giving you the information. I will come back to this. This is first countable, but not metrizable. This is on the real line, but not the usual topology. There's a different topology. It's called first countable, but not metrizable. That means not a metric space, but not a metric space. That means topology cannot come from a metric. Okay, so I will talk about this later on. Anyway, if you go for, you have access as IIT students, because math science NATE, you should you should have access. This is world's one of the premier mathematical societies, American Mathematical Society. This is known as AIMS. And it has a very old journal, you can say, the mathematical reviews. Mathematical reviews basically list all the publications in mathematics, statistics, and mathematical physics, also theoretical computer science. And they review it, published articles, not unpublished, review it. Almost every published article in mathematics, statistics, mathematical physics, and theoretical computer science. So some years back, I think around 15 years back, they started this. This is same as this. This is on the NATE, basically. Before they had the book for mathematical reviews called MR. Now they're having this math science NATE. So since the IIT Delhi subscribes to this, you have access to this. So here, why I'm saying math science NATE, in fact, math science NATE, if you go there, like you can look at somebody's publications, authors, even you can go and see my publication. You can go and see publication of each faculty of our department. Okay, and also you will see a column that sorry. I don't know. I think I'm making the spelling mistake. I think this is spelling mistake. Genealogy. This is basically gives you like the family tree. Okay. So family tree means here who did PhD under whom basically. Who did PhD under whom in mathematics and in which university. Okay. So that way you can figure out that under whom Surgeon Frey did PhD. Okay. That you can see that. Okay. By mentioning that he belongs to my family tree in research. Okay. He belongs to my family tree in research. Okay. That's why I mentioned it. But Surgeon Frey line is very good for examples, counter example. Okay. So later on I will explain Surgeon Frey line. In fact, corresponding to Surgeon Frey line, there is a plane like R square, Surgeon Frey plane. Okay. So you have got definition of first countable space. Okay. So I'm repeating the result. I'm basically copying from Willard. I'm telling you that. Wait a minute. If Stephen Willard, if you go for this, look for pages 70 to 72. Okay. After that also you should look. Because then you have the nets. After that I will teach you nets. So nets that you should look 73 to 76, basically 77. Stephen Willard. Okay. So here the first countable that I'm saying that already I told you this theorem. This is theorem. The way we proved it for metric space, same proof will work. Theorem 10.4, page 71. Okay. Here. If x tau, if it is first countable space, is a first countable space, that means every point has a countable local base, is a first countable space, or sometimes we simply say x tau is first countable. First countable space E subset of x belongs to x, then x belongs to E bar, if and only if there exists a sequence like you did in metric space. There exists a sequence xn in E such that xn goes to x, the way you did in metric space. Okay, but here I should tell you that what problem you may have Okay, this you can prove. Look, in metric space, you have bx 1 by n, usually we take that. But you see that in here, bx, the n is contained bx 1 by n if n greater than n, because this will be smaller. That means basically for, as you see, you are getting a decreasing sequence of neighborhood. Decreasing sequence of neighborhoods. This one actually you will need here in the proof also. But here you see, suppose is a local base at x. Then I see that I can replace it by this w, and if I take this, look, each of them is a neighborhood of x. So this is also a neighborhood of x. Each of them is open, finite intersection open set is open. Each of them contains x, so it contains x, neighborhood of x. Now you see that you get this. This is decreasing. That means Wn like this. If n greater than n. This will need some decreasing sequence in your proof. But I can always assume that your local base is decreasing. That you can assume always. If it is not decreasing, you can do this thing. Okay. So that you will need. That in the proof is there. He is writing the Willard that if necessary, taking this thing in the proof. Okay. So this thing you will need. In metric space, automatically it comes the way we choose. But here, if you don't have it, you do this. Okay. So this is one result. Okay. And that I told you about the continuity. The closer that I don't need that about that. That. Okay. So that I think he's using corollary. I don't know why he's using, but I think he could do it straight that. So, but he's taking why this theorem. This corollary is this is his corollary. But I need only one part, basically 10.5. Okay, but I will put as this as a result. Let f x tau by sigma be a map between two first countable spaces. Between two first countable, these are first count. This usually we say that between two first countable spaces x and y. You don't need to mention topology again. Spaces x and y. Okay. Then got it. Then f is continuous. If and only if whenever xn goes to x in x tau, fxn goes to fx in y sigma. That is sequential convergence, sequential characterization. Sorry. If f is continuous, this will be always true. This is always true, but the question in the other direction, this. Okay. And also, you should check that whether you need both to be first countable. Usually we take this, but you look at the proof, the metric space you did, and see which one actually you needed to the metric space in that. Okay, that you should check that whether you need both of them to be first countable. Okay, so these two results about first countability you need to know. But the question is that some spaces are not first countable, like when you have this, this is infinite. Really, this is uncountable. Let's take that. This is cofinite or co-countable topology, or I have given an example with uncountable co-countable topology, that where sequential characterization of, that is it written in my notes, sequential characterization of closure point and continuity, they are not available, are not possible. Okay, now the question is that I told you that sequential characterizations of closure point and continuity may not be true in general. Sequential characterization of closure point and continuity are not in general possible. Okay. Well, you may think these are bad spaces. No problem with the sequence. Looks. What is the inadequacy sequence? Sequence, first thing is a small thing. Its domain is always n. Okay. So that this is always countable. Domain is fixed. But suppose I go for generalization where the domain, I have flexibility over the domain. It behaves very much like sequence, but the domain has changed. Domain according to my choice. Okay, according to my requirement. In order to do that, then you will see that that is the concept Nate. That I was telling you that Nate. Okay, that is a very powerful tool and a very simple tool. And it is a generalization of this. And Nate, the thing is, this domain is changed. I can change according to my requirement. So that is usually called D, or some people call it Greek letter, big lambda. In order to define Nate, I first need to define directed set. And we will see it's a generalization. So sequence is a special kind of Nate, where the domain is set of naturals. Now the directed set, what do we mean by directed set? First, you need to define a directed set. Now look, recall that when you define the relation, we have particularly two types of relation: partial order
equivalence
and equivalence relation. Okay. So let me recall that what you about the relations you did. First of all, it is reflexive, symmetric, antisymmetric. So usually what we handled, and transitive. Okay. Now you see that, so that I'm coming to this. Okay. So for Nate, first of all, look in the sequence we have what we are actually using. First of all, reflexive comes very it creeps in silently. You do not even realize that you are using. So this is there. You need it. Reflexive. Also, you are using transitivity. That means, look, what does it mean? Transitive. You say this is very natural, because if you have something is n3 greater than n2, n2 greater than n1, then implies that you used always while computing and that manipulating n3 greater than n1. Okay, this is actually transitive that you used. Okay, reflexive, transitive we have used. This one, this actually you didn't use. That you can check that none of them you have used. Actually, it won't be symmetric, it will be anti-symmetric. If n2 greater than n1 greater than equal to n1, n1 greater than equal to, okay, then but this one won't be neither symmetric or anti-symmetric. But you have used another thing often while manipulating. What is that? Look, given this, you always use let n not equal to max of n1, n2. And then, like when you do that, xn goes to x in real, suppose, and yn goes to y, then you say xn plus yn goes to x plus 1. If you need to prove it, actually you need this kind of thing, that n not that, because ultimately here you need, because for this you will need one, you will get a 1 n1, you will get n2, and then you will take the max, for that you will get this. Samajh gaya? Okay, so that you use it. But this means what actually? Okay, look, usually in a director, in a set, I have reflexive transitive, I do not have this kind of thing, max idea. But actually what you are using here, you are having an integer natural number which is bigger than both. Okay, that you are using actually, that given any pair of natural numbers, I can have a third natural number which will be bigger than both. Though I am taking strictly on that, but also in director series usually we use this a notation. This is a notation. Okay, so that you are using reflexive, transitive, and this property means which is co-final. What does it mean? The co-final means complement of final. That means negation of final. Nothing in that means if you have this, there is no final natural number, because if you give me any pair of natural numbers, I can always pick up a bigger one. That means it is a co-final property. Co-final means negation of final. Co-final property. Okay, that you have used. What you have used while manipulating with sequence, that I am telling you, that you use reflexive, that you do not even bother that where you are using. But if you are careful, you will realize transitive, that you often use, and this one it comes this way, co-final. So for directed set, we need these three. That means, suppose I'm taking the definition from Willard 11.1. Look, definition 11.1, page 73. Okay, she's taking lambda. Okay, or we can use D also. A set D, I'm writing D, is a directed set. Directed set if there is a relation, there exists a relation. Look, this is just a notation, less than equal to or this, there is no difference basically. It depends on what notation you are choosing. Okay, it is not the usual less than equal to in the real line on that. Okay, this is just a notation on D satisfying this thing. A, this is reflexive. That is, usually we write small thing lambda, that is lambda this for all lambda belongs to D. He has taken big lambda. B, this is transitive. That is, if, be careful, I have only this notation, I don't have it. So don't use right now this, I don't have it. So if lambda 1 less than equal to, this is just a notation and it is talking, the less than equal to. That's just to indicate, that is a pair of words, just to indicate this symbol. And lambda 2 less than equal to lambda 3, then okay. And finally C, that is if lambda 1, lambda 2 belongs to D, still bigger, that means these will be smaller. I will have to be careful about the notation. Then there exists lambda belongs to D such that this, look, I am not writing greater than equal to, though it will come that later on. And usually we say this is bigger than, but actually since I have only this relation, I am writing this. Okay, there exist. Okay. But here you can see that when you can say that if we have D is a directed set, suppose if D is a directed set, actually I should write now this. This, because only D is not a directed set, you need a relation. If D is a directed set, then often then we use this thing, use this to indicate, use this. Then for lambda 1, lambda 2 in D, we use lambda 1 greater than equal to lambda 2 to denote. Denote, to indicate this thing. Sometimes you use it, but the meaning is this actually, because this is defined. Understand? This is not defined. But if you this way, if you define this will be also direction here. But usually we use also sometimes. But that indication meaning is this. Okay, to indicate that you should know that what is the meaning of this. This is not there, but so you should explain that what do you mean by this. By this we mean this, and this is called a direction. That means directed set means you have on a set, non-empty set, you have a relation which is reflexive, transitive, and cofinal. That is called. So this is called the directed set. Okay. Now, what is net? For net, domain should be a directed set. For net, so suppose now net define. Let X be a non-empty set. I don't need any topology now, like sequence. It's a non-empty set. Sorry. If it's a directed set, Look, sequence is a function on the set of naturals. Then a function f d to x is called a nate. Then a function, I have replaced this, should check this is with the usual order of the real line less than equal. This is a directed set. So I am replacing it in YAM. This is called a nate. And like sequence and f lambda is a function where lambda belongs to D is usually denoted by x lambda. This like xn, x lambda. Okay. Now, so that you have this. So a nate is actually a function, a nate in x is a function from D to x. This is a directed set. When I say that this is a directed set, if you don't mention it is understood, you have a that relation which is reflexive, transitive, and cofinal. And f lambda we denote by x lambda. Like sequence, the whole thing function will often we list by this, like this. The notation, the nate. It means I am listing all the values of the function f like this, like analogous to the sequence, notation for sequence xn, write x lambda. Some people indicate to the right actually this to indicate the directed set. But if you do not need it, you just can simply write x lambda. Okay. So sequence by this definition, a sequence is a nate, but a nate need not be sequence. A sequence is a nate, but a nate need not be a sequence. That I will give you. That's the thing. Okay. Before that, nate introduction. Now look, first of all, to have good examples of nate, I need good examples of directed set. Particularly, I said in topology, the problem was that first countable that sequence was not being able to characterize them. I got sequences inadequate. So that's why my idea of generalizing to nate. So that if you want to have good nates, you need to have good directed sets. Okay. So that now look, just look here. Now start with the topological space. Take x belongs to x. Of course, later on we'll have to define convergence of nate. That will be similar to convergence of sequence. But before that, I should have good examples of nate. So suppose x belongs to nate. X belongs to x, and this is your this thing. Okay, right? Neighborhood systems. But here you give the relation. This look. What do you mean by this? Here I will say you are having two things. U, V, this. There are two neighborhoods of x. I'm saying define u less than, look, I'm defining among the neighborhoods of x. If you have this, smaller neighborhood will be the bigger. If v is contained in u. I told you already in topology, eventually you'll understand intuitively. If you have finer neighborhoods, smaller neighborhoods, then it's a better topology. So that's why you are going smaller neighborhoods. Look, this is the definition. Define this. Got it? U, this thing, less than equal to V. If this is a notation I am defining, then you can check. It's obvious it is reflexive, it is transitive. And what will be the cofinal? Look, that is very simple. That's why I think if you have two neighborhoods, V1 V2, then V1 intersection V2 is also neighborhood of X, and that will be less than equal to this both. So this is cofinal. So this is a directed set. Actually, in topology, we use this directed set. I will say 99.9% time we use this thing, neighborhood system. That's why it is very important. So that, let me write again. So X tau is a topological space. Okay, X belongs to X, okay, and you are taking this neighborhood system, neighborhood filter, Nx. Then Nx is a directed set where for uv belongs to Nx, define u less than equal to v if, okay, so directed set, don't forget. Okay, now look, if you have a directed set, and X, well, so if you have u, by that look x lambda, so I should have a point in xu. But what xu will choose? You can have many things, but actually what we do, that we will later understand. Choose a point xu belongs to u. Any point you choose. Here you are using axiom of choice. You are having a bags of neighborhoods of x, and from each neighborhood, from each bag, you have a collection of bags. Here each bag is a neighborhood of x, and from each bag you are picking up an element x2. So you are using the axiom of choice. Okay, just to remind you. So you pick up a point. So this will be a nate. You can write if you want, but it is understood. Is a nate in x. समझ गया? So why I'm explaining this one we use often 99.9% time. Okay. Now before that, so I will come back to this. I want to see that when in a sequence you write n the usual order. Look, if I write this n greater than equal to n naught, that means which are not, we do not satisfy this, which is natural numbers, they are only finite. That means what I am saying, n not greater than equal to n naught, you can write this. Write n is finite. That you get. I should give you a warning on that. That's why I'm writing in that. I have defined just net. I am not going to do any result, but I should give you a warning that while going for the net, be careful. Here, when you have this will be always finite. But for a net directed set, it may not be true. Let me give an give a good example that you should have known that. I think what is this generation, they do not have the habit of using dictionary. It doesn't matter whether you use Hindi dictionary, Bengali dictionary, or English dictionary, whatever. But dictionary, okay. Here I am calling it as dictionary order or lexicographic order. That I want to explain that why in reality is not true. Lexicographic order. Why dictionary order is also called lexicographic order? Because dictionary has another name. lexicon. That's why from this. Now look, dictionary of terms. I'm just explaining the English. First, you have this 26 letters. But how the words are arranged? First A comes, and then A also you see that first A, if you have another A like this will come, then A, B, then A, C, it will come like this. Similarly for B, it will be BA, BB, BC. Okay. Similarly, it come this. But that doesn't mean what? So lexicographic order, you see that. So if I write this way, suppose this is A, this is B, this is C, like this is Z. Okay. So when now this is your X coordinate like them, but Y coordinate, what are you choosing? First you are having A, so you have this is, you are writing this way, you are going this way, covering all the words. But how it is coming, that already explained. Like A will come, then AB will come, then AC will come. Then when you complete it, then you go to B. Okay. Similarly, you go to C like this way. That is the dictionary. You should understand how it is. Because these days the kids, they always go to the computer. You just click a word and that you get all the meanings on that. You don't need to know even how to use a dictionary. But but it should. You should know how to use. Now look here. Here I can define an order. Suppose like so in YAL you can use an order in the R square in YAL. But I'll do that. Look here I will do this. That's the same thing in the dictionary we use it. This is also dictionary order in R square I'm doing it. I will say define if x1 less than equal to x2. First, if you have this, then you just define, or if x1 equal to x2, but y1 less than equal to y2. If x1 equal to happens to this, that means this is exactly a dictionary. If you have this, you don't need to bother about one. If you have this, you can have this. Then you say this is less than, basically, because x1 coordinate is x coordinate is less than x coordinate of that. Okay, that you get. That means if it is below, like all these columns I am doing in that, that means the column is before, then your element is less than. Okay, right? And if you are in the whereas this means if you it is in the same column, then you look this thing. Look here in the same column, but y2 is bigger than this. Okay, this is that exactly the idea of the dictionary. And R square I can give this. This is not the usual order. Okay, this is not the usual order. Okay, this is called the dictionary order. Okay, now look, you can easily check. This is reflexive, this is transitive, and this is cofinal. If you have this, I can choose this, or I can choose another one here. Okay, so this is a direction. So dictionary order gives a direction. Fine. Okay. Now look, if I say, suppose this, you choose all these things greater than equal to this. Basically, suppose some points. Okay. So suppose this is your x naught, y naught. Now look, but of course greater than equal to this is infinite, but for less than this, which are this, in R square, look, but x, all this here, there are infinitely many. If you go for R square, in dictionary you will get finitely many words, Okay, but point in R square, if you go, this will be infinite collection. Infinitely many will be less than this in R square. In dictionary, we may say if you have finitely many words because of you have only 26 letters. Okay, but words, if you do not bother about the meaning, you can strictly, then you can also what infinitely many words you can construct. That's the concept in mathematics. Talking about words in algebra, you have it. Okay, so if you do not bother about the
Yes, sir.
meanings, if you just say if I will place the letters you can place many things. You have 10 letters, 11 letters, 12 letters, like that. So you can, that way you can have infinitely many words. But even then, if you do not like that, you go for R square. But then you see that this will be infinite. So that for the net directed set, don't be misled, but that if you write greater than equal to these or less than this, rest will be finite. Rest also may be infinite. That means you may split the set, directed set D into two infinite sets. Okay, so that is very vital. Now the thing is that, so next time I'll do it. Now I think again you can read, so that you should have directed set what I am suggesting, directed set. Then you look at the definition of net, what I have taught, and also again think about dictionary order. Look, for the definition of directed set net, I do not need any topology. I just given a good example of directed set in a topological space. Now I need to link in a topological space. That usually we take this. This is a directed set. My God. Now next time I'll do it Monday. If I get a net in a topological space, because it's a generalization of sequence, then what will I will mean by convergence of a net? Convergence of a net. Okay. That's I need to explain. That is exactly I need. Convergence of net. Also, I won't need often on that, but since giving to sequence, you have that in the wheel at same page 73 in the bottom line, you will see that sequence you have subsequence. So how will I define net? Given a net, how will I define a subnet? It looks that it is right now that a concept is difficult. Concept is not difficult. It's very simple. It is simpler than sequence. Let me tell you, and it gives you a lot of flexibility. Net, subnet, that I will explain. But also you just need this convergence of a net. Okay, and after defining net, we'll see that net characterization of closure point and continuity both are available. It doesn't matter what is your topological space. You don't need any first countable anything. For every topological space, I will have sequential net characterization of closure point and continuity. समझ गया? That I will do that. At best, occasionally I may need to assume to be house drop, but that is a very nominal assumption. In the good topological space, need to be house drop. Okay, if you want to avoid pathology, that also is not all the time you'll need it. So next time I will talk about net. In between, you study directed set, net, and also I think already you fixed with, but again you can talk with Saurabh. I think you have about the tutorial. Okay, Saurabh circuit. I think he has given already fixed two groups and that. Okay, but again this is between you people and Saurabh, that how the tutorial will be handled, and you should ask him the questions and that often. In fact, outside tutorial, you can always send him a message. You should have his email account. That will even IIT email account. You can see that his entry number using that. You can send him that. Okay. And some of you, I think, are onboarded and he is in the campus. So you can talk to him personally also if you want. Okay, he's a very promising scholar. Let me tell you that. I think eventually he will turn out to be a very good mathematician. Okay, so it's good. In a sense, you are lucky that you have got him as a tutorial teacher. Okay. Okay, see you on Monday. Okay, bye.
Sir,
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 thank you, sir.
sir, please,
Have
sir, please upload
Upload what?
the notes for these topics.
Notes.
Yes, sir, like we get in the metric spaces.
You want me to write the notes? I have told you already. You go for Willard. You should have Willard. I told you the page. I will actually copy these things. Huh?
Okay, sir. Okay, sir.
See, you just see that. If you still have problem, then I will upload the notes. Okay. But I am giving the Willard Indian edition is available. I think in the net you will find it. Okay. And Willard you should have. And I am telling you the page number theorem. You should read that. Okay. And if you want, still I can upload these notes on that. Okay. But right now I am giving more time. I am explaining the concepts, ideas. I am not going into too many results on that. Okay. So that you should spend more time in understanding the concept of topology, concepts and the definition, all these things. Okay. Otherwise, later on you'll have the problem. So I will, if needed, I will do that. Okay. Okay. Bye.